We'll be discussing about another stability analysis technique in the frequency domain named as Bode plots. So coming to the introduction, frequency response is considered as a steady state response of a system to a sinusoidal input. So here, as you can see, we are giving an input, a sinusoidal input for a system. The response, whatever I am going to get out of this input, is termed as steady state response. So in frequency response methods, the frequency of the input signal is varied over a certain range and the resulting response is studied. So we will be changing the frequency of the input sinusoidal signal and the corresponding output is noted down and it is tabulated for analysis. Now coming to the basic concepts of frequency response, in the steady state, the sinusoidal inputs to a linear system generates a sinusoidal responses of the same frequency, and even though these responses are of the same frequency as the input, they differ in the amplitude and the phase angle from the output. So these two are the things which is going to change in the output response, that is amplitude and phase angle. So these differences are determined with respect to the frequency value and it is treated as a function of frequency. The sinusoids, each of these sinusoids, whatever we have, can be represented as a complex number, or it is also called as phasors. And the magnitude of complex numbers, as you know, is the amplitude of the sinusoid and the angle of the complex number in the phase angle of the sinusoid, which is represented as m1 cos omega t plus phi and m1 angle of phi 1. So where m1 is represented as what? It's the magnitude, and phi is taken as the frequency value or the angle value with respect to the frequency. So this is the magnitude and this is the phase value with respect to the frequency omega. So a system which causes both the amplitude and the phase angle for the corresponding input always can be changed, and therefore the system itself can be represented by a complex number. Thus the product of the input phasor and the system function yields the phasor representation of the output, which we can represent with an example. Okay, now let's take a mechanical system which has a spring, a damper and a mass. So here the input is represented as m naught cos omega plus phi naught, and the applied force F of t is taken as mi cos omega t plus phi I. So if the input force F of t is sinusoidal, the steady state output response x of t of the system is also a sinusoidal with the same frequency as the input. So the magnitude and the phase value corresponding to the input and with respect to the system is represented as mi of omega, which is nothing but the magnitude of the input, phi I of omega, which is the phase of the input, and this is the response of the system, which is output response is represented as m naught omega and the phase value is represented as phi naught of omega. So assuming that the system is represented by a complex number, we can have the magnitude value as m of omega and the phase value as phi of omega. So the output is found by multiplying the complex number representation of the input by the complex number representation of the system. So this input is multiplied with the response of the system in the complex form to yield the output. So which is represented as m naught of omega, phi naught of omega is equal to m omega into mi omega angle of phi omega plus phi I of omega, where m naught of omega is the magnitude response and phi omega is the phase response, and the combination of the magnitude and phase frequency response is called as the frequency response totally. Now this frequency response can be determined by using various frequency domain plots termed as Bode's plot, Nyquist plot and Nichols chart. So in our syllabus we will be discussing about Bode plot. So in the first module we will study about Bode plots, and in the fifth module we are going to study about the Nyquist plots. Now coming to Bode's plot, a Bode diagram, it basically consists of two graphs. One is a plot of logarithm of the magnitude of the sinusoid transfer function. The other is the plot of the phase angle. and both are plotted against the frequency on a logarithmic scale. So this is the plot of magnitude and phase. The first one represents the magnitude plot wherein the reference is taken from 0 dB, and similarly the angle here is represented by taking the reference to be minus 180 degrees. So these two are the plots which is drawn using the semilog graph sheet. So this is the graph sheet, semilog graph sheet, which we'll be using to draw the Bode plot for the stability analysis in the frequency domain. Now, so as you people know, in a semilog graph sheet, one block is considered to be 1 decade. Now coming to the basic factors of the transfer function. So whenever we start any of the plots using Bode diagram, we are supposed to be aware of the basic factors of a transfer function. So the basic factors that verify the very frequently occur in the arbitrary transfer function are gain k, integral and derivative factors, which is represented as j omega, right? So first order factors, which is represented as j omega t plus 1, and similarly quadratic factors, which are represented as 1 plus 2 zeta j omega divided by omega n plus j omega divided by omega n whole square plus or minus. Power could be either you can have this in the numerator or in the denominator. That means you can have either a pole or a 0 in your representation. Okay, so four factors are gain, integral and derivative factors, first order factors, and quadratic factors. So let's understand these four factors by taking an example here. So g of s is given as 20 into 3s plus 1 divided by s into s plus 1 into s square plus 5s plus 2. So this is the open loop transfer function what I have, for which I need to determine all these factors. Now according to this, if you can see, the constant 20 is taken as the gain, and the value 3s plus 1 is treated as first order factor. So s is treated as your integral, and s plus 1 is treated as your first order factor, and this is your quadratic factor after replacing s with j omega. Now first we will understand how to represent this constant gain k in the logarithmic form. So the log magnitude curve of a constant gain is a horizontal straight line at a magnitude of 20 log k decibels, and the phase angle of the gain k is 0 because it's a numerical value what we are going to have with 0 phase. And the effect of varying the gain k in the transfer function is that it raises or lowers the log magnitude curve of the transfer function by the corresponding constant amount, but it has no effect on the phase curve. This is about gain k. Now let's see how we can represent this in the logarithmic form. So if k is equal to 5, for example, then 20 log of k is treated as 20 log 5, which we are going to get it as equal to 14 dB. Okay, now let's see how I can represent this using the semilog graph sheet. So here we are going to represent the logarithmic scale of the constant gain k as 14 dB by just representing it by a straight line like this. Okay, now this is about your constant gain k and its representation. Now coming to another example, if k equal to 5, now let's check with the phase value. So phase value is 0, it is represented as 0 degree here again with a straight line. So this is how the gain value, that is magnitude value and phase value for a constant DC gain of a system is represented. So it's represented with a straight line. Okay, second factor is called as integral or derivative factor, which is represented as j omega or 1 by j omega. Now for this derivative factor, g of s is taken as s, so where s is replaced with j omega. Okay, now similarly, if I take the magnitude for this derivative factor, it is represented as 20 log of omega. Okay, that is 20 log of j omega is nothing but equal to 20 log of omega. And phase value, this is a table which is showing you the value in dB for different frequency values listed as 0.1, 0.2, 0.4, 0.5, 0.7, 0.8, 0.9 and 1, and these are the values in decibels which I am getting as a magnitude for the derivative factor. So it is minus 20 dB, minus 14 dB, 8 dB, minus 8 dB, minus 6 dB, minus 3 dB, minus 2 dB, minus 1 dB and 0. So just to quote an example how by varying the frequency the magnitude changes for a derivative factor is shown here in the table. Now coming to the slope, okay, slope is nothing but taken as 20 decibels per decade for a derivative factor. It is plus 20 decibels per second because it is for one decade from 1 to, that is 0.1 to 1. It is taken as equal to what? 0 minus 20. So minus of minus 20 becomes plus 20. So slope is considered to be 20 decibels per second for a derivative factor. And slope for octave, okay, it is considered as 66 dB. And similarly the phase value is taken as angle of j omega is nothing but equal to tan inverse of omega by 0, which you will get it as equal to infinity. Tan inverse of infinity is nothing but equal to 90 degrees. So just remember this, the phase value for a derivative factor is nothing but equal to 90 degree and its magnitude is always 20 log of omega. These things you must remember to draw your Bode plots. Now this is how a slope for a derivative factor is drawn. So it is 20 decibels per second. So here as you can observe, we are drawing a slope with a phi value is nothing but equal to tan inverse of omega by 0, which will give you the phase value as 90 degree, which I am just representing it with a 90 degree line. Okay. Now let's move to the next factor, which is termed as the integral factor, which is taken as 1 by j omega. So when we are going to express this integral factor in the reciprocal form, we are going to get the magnitude value for an integral value with minus 20 decibels per decade as equal to magnitude of 1 by j omega, which yields the value as minus 20 log of omega. This is our magnitude value. Now coming to the phase value, g of j omega is taken as minus tan inverse of omega by 0. So it is nothing but equal to minus 90 degree. So in the previous slide you saw that phase angle for an derivative factor is plus 90 degree and magnitude was 20 log of omega. But for an integral factor it is minus 20 log of omega and minus 90 degree. And this is how the slope goes for a integral factor which is represented as minus 20 decibels per decade. So please to observe here from this point to this point, this is the slope which is extended. And phase value is taken as minus 90 degree, so it is represented here with a straight line. This is about integral and derivative factors. Now similarly, if we consider the other factors of the transfer function, we have a first order transfer function which is represented as j omega plus t plus 1. So magnitude of this is taken as 20 log of 1 plus j omega t, or it is nothing but equal to 20 log of root of 1 minus omega square t square, or with the lower frequency, that is if omega is very much less than 1 by t, then m of omega is just taken as 20 log of 1, or it is taken as 0. So for higher order frequencies, m of omega is taken as 20 log of omega t because 1 becomes 2 less. So 1 plus a higher value can be just treated as omega square t square itself. By taking root for this, we can just take it as equal to 20 log of omega t. Now coming to the phase value for a first order factor, j omega t plus 1, phi of omega is taken as tan inverse of omega t. So when we take some values for omega 0, 1 by t and infinity till infinity, the value of your phi of omega varies like this. So tan inverse of 0 is 0, tan inverse of 1 gives us the value is 45 degree, and tan inverse of infinity is always 90 degree. So it depends upon the value of omega in this case. Now let's see how we can represent them using the simulograph sheet. Now this is about your plot. Okay, so for a factor like this, we have the slope as plus 20 decibels per second. Okay, and the phase value here, it is taken as 0 degree, 45 degree and 90 degree, and you will vary your frequency and you will join like this. So this is how the phase plot you're going to get for a factor. Okay, now coming to the first order factor, another factor which is represented as 1 by j omega t plus 1. So here for this, since it is minus 20 log of 1 plus j omega t, magnitude value for omega less than 1 by t, very much less than 1 by t is 0, and for higher frequencies, m of omega is taken as minus 20 log of omega t. And phase value, as usual, it is, since it's a reciprocal, you will have a negative angle here, so phi of omega is taken as minus tan inverse of omega t, and when omega is equal to 0, phi of omega is tan inverse of 0, and when omega is equal to 1 by t, it is taken as minus tan inverse of 1, and when omega is equal to infinity, it is treated as minus tan inverse of infinity, that is minus 90 degree. Now similarly, we will draw this response here in the similar graph sheet. Okay, for g of s is equal to 1 divided by s plus 3, for a decade we are getting the slope as equal to minus 20 decibels per decade as shown here. Okay, and similarly the phase value here is represented as 0 degree, minus 45 degree and minus 90 degree, and we will join all the points to. Now let's take an example. Now here we are taking an example where we will try to draw the Bode plot for the transfer function, which is given as g of s is equal to 20s divided by s plus 10. As you can see here, we have a DC gain as 20. We have a derivative factor followed by a factor in the denominator, simple factor in the denominator factor. So in the time constant format, if I represent this by taking 10 as common, this same transfer function can be rewritten as 2s divided by 0.1s plus 1. Okay, now according to the comparison, the factors what I have is gain factor k is equal to 2, derivative factor is yes, and you have to list out the factors like this always for every problem, and first order factor in the denominator in the form as 0.1s plus 1 inverse. Okay, so after identifying the factor, we need to find the magnitude and phase value for all these factors which is present in your transfer function. Let's see how we can evaluate. Now first we are trying to find the magnitude value and phase value for the gain factor k equal to 2. So in decibels, the magnitude of the gain factor k equal to 2 is taken as 20 log of 2, which you are going to get it as equal to 6 dB. And phase value, as you know, it is 0. Now similar thing we will evaluate for the derivative factor s also. So in decibels, so usually by taking the value of t as equal to 0.1, we will evaluate this. So it is 20 log of omega t is 0.1, right? So it is 20 log of omega, for which I am going to get the value of the magnitude as equal to 20 decibels per decade for a derivative factor. And similarly, for a first order factor, if omega is less than, very much less than 10, then it is taken as 1 divided by 0.1 j omega plus 1. Okay, and for this we are going to take the value as minus 20 log of 1, which is equal to 0. And for omega greater than 10, it is just taken as equal to minus 20 log of 0.1 omega, or it is nothing but equal to minus 20 decibels per decade. So first we have tried to find out the magnitude value for all the factors. So list out like this one by one, okay, in the similar way. Now coming to the magnitude representation for this particular value of g of s, first we are representing a straight line for the DC gain with k as equal to 2 as equal to 20 dB slope. We are drawing first. Okay, then we are drawing the 0 reference line, minus 20 dB. Okay, and then we are just adding them together like this, 20 dB, and we are plotting it. Okay, now let's see how we can draw the phase plot. So now for phase value is taken as angle of j omega is equal to angle of 2 plus angle of j omega minus angle of 0.1 j omega plus 1. So you know that angle of 2 is 0. Okay, so it is tan inverse of 0 will be 0. So tan inverse of omega by 0 will give you the value as 90 degree, and minus tan inverse of 0.1 omega we have. So it is nothing but equal to, generally g of j omega is taken as 90 degree minus tan inverse of 0.1 omega. Now what we will do is, I will take different values for omega in a decade and I will find out the phase angle value. So I am starting with the omega value as 0.1 here. So for 0.1, the angle what I am getting here is 89.4. For 1 it is 84.2, and for value 5 it is 63.4. If omega is equal to 10, I am getting the value of phi of omega as 45 degree. For 20 it is 26.5. For 40 the angle is 14. For 70 it is 8. And for 100 it is 5.7. And for a decade, that is from 100, if I take a decade, it's 1000. The value what I'll get it as 0.5. Now let's plot the phase value of this particular open loop transfer function using the similar graph sheet. So first list out all the points, correct? For point 1 it is 89.4, for 1 it is 84.2, 63.4, 45, 26.5, 14, 8, 5.7 and 0.5. Now, so you are supposed to join all these dots, okay, and extend like this. Okay, one at infinity it becomes 0, so I'm just representing that with a 0 line here. So this is the magnitude plot what I have got for the given example. I hope all of you followed this. So please do understand this properly. If you solve one proper like this, any question they might give you, so basic concepts what you need to remember is, you should know how to identify the factors and then how to represent them using the magnitude and the phase value, and by varying the frequency we should note down the corresponding magnitude and phase response value. In today's session we have discussed about the frequency domain analysis and how to correlate the time domain value with the frequency domain value you have learned, followed by the different types of the plots like Bode's plots, Nyquist plots and Nicholas plots was listed. And in today's session we have discussed about Bode's plot, which is an important plot used to analyze the stability of the system in the frequency domain, and we have dealt with the different factors involved in the Bode's plot representation and with an example. I hope the session was interesting, and these are some reference books which are listed in the slide, and you can refer them for further details. Thank you all. Have a nice day. Jai Shri Gurudev.